So welcome to another lecture of the series of modeling and design of power semiconductor devices. So we have started with the linear converters, switch mode power converters, then the basic second order DC-DC converters, then second order DC-DC current converters, fourth order DC-DC voltage converters using second order DC-DC current converters. Then we also saw isolated DC-DC converters. We saw all the topologies: forward, flyback, push pull, half bridge, full bridge, dual active bridge. So now let's start with the power semiconductor devices. So the first power device that we will analyze today is a power diode. So in this figure, so here you can see that this is the constructional diagram of a power diode. So it's very similar to a signal diode. The only thing is we have P plus, N minus and N plus regions. So the basic and over this substrate we have metallization. So here you can see the metal. This is called as the metal at the cathode, and the top one here is the metallization of the anode. So top one is the anode terminal A and the bottom one is the cathode terminal K. Below the anode metallization layer we have a region of P plus doped region, that is a heavily doped with P-type material. Then we have a N minus and N plus. N minus is called the substrate, which is the cathode, and N plus, and N minus is the drift region, and the P plus region is called as the anode. So power diode is a majority carrier semiconductor device which has characteristics very similar to a signal diode. The only change lies in the construction aspect of it. So the representation of a power diode is very similar to a signal diode. This is the circuit representation. This is anode, this is cathode. This is the voltage VAK plus minus, and this is the diode current ID. So this is the signal representation. So this is the circuit representation of the diode, and the right side figure is the construction diagram of a diode, of a power diode. Now if we just see the types of power diode, so basically there are three types of power diodes. So the basis on which they are classified depends upon their power rating, which is the voltage and current rating, and it is also dependent on the speed of operation of it. We will see it in this lecture. So the first type of power diode is called as a rectifier diode. So what is a rectifier diode is? It is used mostly in the AC mains. Means it is used for rectification purpose. So we'll just draw a I'll just draw a full bridge diode rectifier. So this is the diode bridge. So what we do is we give a AC supply across these two terminal, and then we get a DC across this, which is a fluctuating DC. So V0 is of this nature, and this is V in. So V in is of sinusoidal nature. So these are the diodes D1, D2, D3, D4. So V in is nothing but 230 root 2 sine of 100 pi t equals to V in. So basically what happens is, in this specific application where the diode is used only for rectification purpose, so the basic before going to this, the basic principle of operation of power diode is very similar to a signal diode. It means when the voltage across the diode, which is VAK, is positive, means the voltage of anode is more than that of the cathode, then it becomes forward bias, and then it conducts the current. In the either case, it acts as a reverse bias, and it does not conduct any current. So diode is a uncontrolled semiconductor device. So basically what happens is, even if VA is not less than so even if under the circumstances where VA is not greater than VK, but still the current in the circuit forces the diode to turn on, then in that case the diode current ID will force the diode to turn on. So this is the working principle of power diode, very similar to a signal diode. So in this case, what happens is in this full bridge rectifier, so in the positive half cycle, diode D1, D4 conducts. In the negative half cycle, diode D2, D3 conducts. So basically, what is the voltage across the diode when it is turned off? So basically, let's say if it's positive half cycle, D1 and D4 conducts. So basically it becomes like this. We'll draw a short circuit, and then this is the open circuit. Again here is the open circuit, and then there is a short circuit like this. So let's say this is of this polarity. So this is plus with respect to this, and this is minus, and this is V0. So what happens is this is VD2, where this is plus, this is minus, and this is VD3, this is plus, this is minus. So voltage across the diodes, across any diode when it is turned off, is nothing but V diode is nothing but the peak value 230 into root 2. So basically these type of rectifier diodes are rated for high voltage rating. So they are rated for high voltage blocking capability. This type of rectifier diodes, and also they are used for high current carrying capability. High current carrying capacity. These are rectifier diodes. And the speed of operation is at what speed the diode operates. So the diode turns on and turns off at a frequency equal to the supply frequency. That's why they are slow diodes, because they operate at power frequency, which is 50 Hertz. So they are slow in nature, but their voltage and current rating is higher. So these type of diodes are called as rectifier diode. They are used in for AC to DC converters. So then we see the second type of diode, which is the Schottky diode. So Schottky diode is basically used in a DC-DC converter, DC-DC SMPS or SMPC converter. SMPS means basically switch mode power conversion devices. That's why if a diode is used in a SMPS application where it is used to give a DC supply to any auxiliary circuits or any power electronic circuit, that diode is called as a Schottky diode. That's why if it is used in SMPC application, means it operates at high speeds. That is at F equals to in the range of tens or hundreds of kilohertz, not 50 hertz. They operate at very high frequency. They have low voltage and current rating. And also low power, thus low power. And also they have low on-state voltage drop. Low on-state voltage drop. That is typically less than 100 volts for silicon and greater than 100 volts for silicon carbide devices. So these are the characteristics of Schottky diode. They are used in DC-DC converters where SMPC application is preferred. The third type of diode is called as fast recovery diode. So fast recovery diodes are used for DC to AC converters or inverters. That's why. So, and basically they operate at moderate power rating. Moderate power rating in a few of kilowatts, multiplies of some kilowatts. The speed of operation is fast, or they operate at F equals to 1 kilohertz to 50 kilohertz range. And the Schottky diodes operate at from tens to hundreds of kilohertz. So you can say this is also fast and this is also fast, but Schottky diodes are faster than fast recovery diodes. Means they are fast diodes. So these were the basic three types of diodes based on the voltage current rating, and based on the voltage current power rating, and based on the speed of operation of the diodes used in different applications. Now we'll see the VI characteristics of diode. So the VI characteristics of power diode are very similar to that of a signal diode. So first we'll draw on the y-axis, we have current ID, capital ID or small ID, whatever you want to denote. I am writing small ID. This is the VAK, V anode to cathode. So what happens is, as you know, that the diode will start conducting when VAK is greater than some threshold voltage. Let's say this is some VTH, that is threshold. So after beyond this voltage, what happens? The diode starts conducting and the current starts rising gradually. So here you can see like this, the current will rise. Okay, this is the VTH, threshold voltage. So if you reduce the VAK, what happens is the VI characteristics fall and it goes beyond the negative x-axis, that is the voltage across the diode becomes negative. It is like this, it goes down, there is some constant amount of current, leakage current flowing through the diode. So this is in the blocking region. But what happens if you further go on increasing the voltage across the diode? It will go into breakdown region. This is a breakdown region. So we'll split this region, we'll call this region as breakdown region. This region is called as the blocking region. And this region is called as the conduction region. So these are the characteristics of the VI characteristics of a diode. So this current is called as the leakage current. This is the leakage current. And what happens is, if we from the threshold voltage point, if we draw a straight line like this, where we approximate the VI characteristics, this knowledge, the VI characteristics in the conduction region, we can say that this slope is nothing but the resistance. Y by x means it is nothing but inverse of resistance, 1 by resistance, this slope. So here what happens is, we can approximate the model of a diode in the conduction region to be a resistance with some threshold voltage. So the on-state equivalent circuit is of a power diode is on-state equivalent circuit of a power diode is like this. So means this is approximated as this is RD, this is plus minus VTH, and this is VAK from here to here, plus minus, and this is ID. Similarly, here it is anode, cathode, VAK plus minus, and this is ID. So RD we can find by approximating the IV characteristics in the conduction region by getting the slope of the curve. So these are the IV characteristics of a diode, or you can call it as output characteristics of a diode. Now apart from these characteristics, we have to understand the other important characteristics of power diode, which are called as the switching characteristics. So the switching characteristics means that in the VI characteristics, we plot voltage versus current in a diode, or the output characteristics, how the current varies with the applied voltage across the diode from anode to cathode. But switching characteristics means the individual plot of the voltage versus time and current versus time of a power device, which is a power diode. So that is the switching characteristics. So to study the switching characteristics, we should see how the diode should be connected in a circuit, in an electrical circuit. Means, and in the electrical circuit, the diode should turn on and turn off. Then only we can able to plot the voltage versus time graph and current versus time graph of the power diode. So first we'll make a switching, for switching characteristics we'll make the circuit. So here we are studying now switching characteristics. For that we'll have a circuit. So that circuit should have on and off states of the power diode, and we should also have a load. Means the circuit should be, means the diode is able, means the circuit is able to provide power to a load, and the load defines the current, basically the working current or the steady state current. So let's say the diode is turned on. So what should be the current through the diode in steady state? That is defined by the load current. So let's define a constant current. So for a constant current, let's assume that it's inductive in nature. So we'll make a circuit. So here it's a DC source V in plus minus, and let's say there is a switch S, which is a test switch. Now we want to see the VI characteristics of a diode. Let's say diode is connected like this. This is anode, this is cathode, and this is ID. And across this diode, let's connect a load. So here this is L, and this current is IL. So the switch can be on and off like this, 1 0 1 0. So let's quickly draw the characteristics. Let's say this is the switching pulse, 1 0, like this. This is S, 1 0 1 0. And if we just draw this behind, we can draw the voltage or current waveforms of different circuit elements, like the switch and diode. So when the switch is on, what happens is the positive terminal gets connected to the cathode of the diode, and the anode gets connected to the negative terminal. Means it will be reversed bias. In that case, diode will be turned off and the switch will be on. So thus the inductor or the load L will get magnetized through the input current. So let's say this is VL, like this. So let's say that we'll draw VL. This is VL. When the switch is on, VL is V in, like this. This is V in, this is V in, this is V in. And when the switch is off, what happens is, let's assume that the inductance is very high. If inductance is very high, let's assume that the inductor current is almost smooth waveform like this. More the inductance, more smoother will be the current waveform. So what happens in the case where the switch is off? So despite any uh, positive voltage applied across the diode will be forced to turn on. Why? Because here the current in the inductor is being discontinued, and as the inductance is very high, the current will be very smooth. So what happens is inductor in a current is changing suddenly, which should not happen ideally. Why? Because a very huge voltage drop will be induced across the inductor, which will be observed at the switch. Means a huge voltage drop will be observed across the switch, and the switch, which can be in this case a MOSFET, will be damaged. Let's assume that as the switch is used for test purpose, let's assume it to be an ideal switch having ideal characteristics, because we are using that switch as a test switch or a test device to plot the characteristics of a switching characteristics of a diode which is under test. So what happens, the current IL will force to flow like this, and thus what happens, ID equals to IL, and the diode will be forward bias. If the diode is forward bias, the voltage across it is 0, and the diode current equals to the inductor current, and the voltage across the diode will be what, 0. So voltage across diode equals to voltage across inductor, so it will be 0 0 like this. So VL we have drawn. Let's draw quickly IL. When the switch is on, the inductor is getting magnetized. So VL is L di by dt. So I is 1 by L integral V dt. What is integral V? In this case, V is constant, that is V. Integration of constant is a rising slope waveform. So it will be like this. Then in the next case, what is the voltage across inductor? Integration of 0. So what happens is, the current tends to fall. And before even it falls, what happens in the next cycle, again it rises. So it's a fluctuating current, IL. Now if this is IL, we can draw the current through the switch, IS. So IS equals to IL when the switch is turned on. Simple. So chop the inductor current waveform and bring only the on value down. That will be the current through the switch S. What will be the voltage across the device, Vs? When the switch is on, voltage is 0. When the switch is off, what is the voltage across the device? When the switch is off, diode is turned on. So this will be connected short across the, so this point will come here, and in that case voltage across S equals to V in. Let's say this is Vs minus plus. So Vs equals to V in. This is V in 0, V in 0. This will be the voltage across the switch. Now we have to draw. Let's draw the voltage across the inductor is drawn. Everything is drawn. Let's draw the current through the diode. Voltage across the diode and current through the diode quickly. The voltage. Let's draw VD first. When the switch is on, diode is turned off. So voltage across the diode, VAK, where this is plus and this is minus. When the switch is on, VAK equals to minus V in, because the polarity is reversed. So it's like this. This is minus V in, and minus V in. And when the switch is off, the diode is short circuited, means the voltage across it is 0, 0, 0. So the waveform of diode voltage is like this. And the last waveform is the waveform of the diode current. Diode current ID equals to IL when the switch is off. And in the either case it is 0. Why? Because it's reverse bias. So it's like this. Chop off the inductor current waveform and take only the off wala value. It will be 0, 0 like this. This is ID. So this is how should ideally be the waveforms for the diode under test. So now let's plot the transients. These are the steady state waveforms. This is how the current and voltage should be in under steady state. But we have to see the characteristics especially during the transition period, that is during turn on and during turn off. So what people did, people did experiments. They plotted the current through the inductor and the voltage across the current through the diode and voltage across the diode at a very small time scales to observe how the waveforms are varying with respect to time. That is just to capture the transients. So, and what they observed is that the waveform looks like this. So I'll directly draw the waveforms. Let's say first we draw the current through the diode. So this is time and this is ID. Similarly, say this is VAK or VD and this is the zero axis for the voltage time. Let's say we start from the tangent when the switch is off and it is just about to get turned on. So basically what happens before that transition, there is a steady state. So what is the steady state for the diode? Because now we are plotting only the diode waveforms ID and VAK. So what was the previous steady state? The voltage across the diode VAK was minus V in. So let me write here VAK instead of VD. So VAK was minus V in. That was the previous steady state. So this waveform starts from minus V in value. So means diode was reverse bias, and you know that during the reverse bias diode has some current, that is this current leakage. IL is the leakage current. So the current starts from the leakage current value. It's a very small negative value, so it starts from the like this minus IL leakage value. Then let's say at some moment you give the switching pulse to it, and this is the moment. S is equals to 1 at this moment. At this moment S equals to 1. So what happens is we have to draw the characteristics as per this test circuit. So there is a inductor in the circuit. Inductor is an energy storage element which means that it stores the energy inside it in the form of electromagnetic waves or electromagnetic storage. And as it is a storage device, it means that its current, specifically for the case of inductor, current through inductor is a state variable. What is the meaning of state variable? A state variable is a quantity which cannot which does not change suddenly or directly goes to steady state. It has some incurred delay with respect to it. And in the case of inductor, the nature of current will be governed by what is the voltage across the inductor. Thus, the current through inductor is a state, not the voltage applied across the inductor. So based on the nature of voltage applied across the inductor, the current is governed. Means here the current to the inductor is a state. Means the whole idea why I am saying this thing is because in this test circuit we are assuming that the input voltage Vin is constant and the switch is ideal, and we are testing the diode. We want to plot the IAK versus time and ID with respect to time and VAK with respect to time, and based on this circuit configuration. Okay, so we have a state, that is a current. So basically what happens is the voltage waveform means the voltage across the inductor current will govern the current through it, and whenever the switch is on, in that case the inductor current is equals to the diode current. Okay, so in this case let's see how the characteristics or how the ID and VAK varies with respect to time. So at this moment S equals to 1, the switch is turned on. So what happens when the switch is turned on? The diode has to be in, means ideally the diode has to reverse bias. Actually there is a mistake here. S equals to 0, means here that the previous steady state was a switch is turned on. So switch is, what I directly write, S is on. Now here S equals to 0 command came, means initially the diode was, so initially the initial steady state was that the switch is on. If the switch is on, the diode was in reverse bias, and in the reverse bias the voltage across it is minus Vin, which is here, and the current through it is minus IL, which is the leakage current, and the diode is turned off. Now the switch is turned off, means the diode has to turn on. So when the diode has to turn on, the current through it should rise and the voltage across it should fall. And as per this characteristics, so when the diode is off, the diode has to turn on, it has to have some on-state drop associated with it. That is based on this on-state equivalent circuit, which I have drawn here. And means there has to be some drop here across it in steady state. Now let's see how transiently how it happens. So this voltage across it should fall. So means what happens is the voltage should start fall. But here, as we have a state, so the current through the diode and the voltage across diode will, so basically the current through the diode will be governed by the inductor current, especially during the off period. Means off period means the off period of the switch, not the diode. So now the diode is going to turn on, and ID equals to IL, which is a state. So what happens? Current has to rise and voltage has to fall. So what happens? The voltage starts falling linearly. Voltage starts falling linearly. Say it crosses 0. And this is the steady state value of the this thing. Say this is a VF, forward voltage drop. So here I write forward voltage drop. VF is the forward voltage drop of the diode in steady state. So ideally this voltage waveform should ideally cross like this and it should settle here. But what people observed is the voltage goes on rising. Similarly, what happens in the current waveform? Current should rise. So from this minus IL value, current rises. It becomes 0 and then it rises. What people observed is that here the till the current IL, so let's say that this is the steady state current of ID, this particular portion. So let's say this. One second. Yeah, this should be the steady state current through the diode when the switch is off and when the diode is on. So let's say this is the IL. I am drawing only the average value of it. Let's not draw the triangular bound of it. So what happens is the current goes on rises, and as it hits this value, it settles down to the value like this. But till the current rises from its steady state off value to the steady state on value, how is the voltage waveform across the diode is that it rises beyond, the voltage waveform rises beyond the steady state value, and as this hits this steady state value, the voltage falls and then it becomes equal to the steady state value. This people observed, and what they observed is that for a typical power diode, this overshoot is usually in the range of 30 to 40 volts. So this phenomenon is called as forward recovery of the diode. Forward recovery of the diode means that there is an overshoot in the voltage waveform or the voltage across the diode. That is due to the property of the material of it. So let's say that now the steady state has achieved, means that the switch is turned on now. Now there is steady state. Now this IL is almost constant, and voltage across the diode is also constant. It is the on state drop. This is VF. Let's say at this point some command came to turn it off, means to turn on the switch or to turn off the diode. Say at this point S equals to 1. So I'll write like this. This is when S is off, and this is again when S equals to on. This is the transition period, and this is the transition period during on and off cycle. So let's say this is the long time, so this waveform goes till here, and at this point some command is there. So here also voltage waveform goes here, and there is some command. So now the diode has to reverse bias, means it has to turn off. Turn off means current should fall and it should reach to the steady state value. What is the steady state value? That is the IL, leakage current, and voltage should rise, means voltage should go to minus V, means ultimately voltage should rise in the negative direction, or I can say that voltage should fall. So one more thing, this delay time. So now, as I said, that it's a transient, it has a state. Inductor current is a state. Being the presence of state in a circuit, things won't change from one steady state to other steady state instantaneously. There is some delay associated with it, that is called a transient, and there are some times associated with it. So the time from the command of on switch on time to this time is called as the time T1. T1 is from the on switch off command or diode on command till the peak or when current hits the steady state. This is T1 time. T2 time is when the T2 time is for the overshoot of the diode voltage. This is T2, and this is total T on. Here I am saying now on with respect to the diode. So T on, that is the total turn on time for the power diode, is T1 plus T2. T2 is the time for the forward recovery, and T1 is the time for the delay, that is for the rise and fall of the voltage and current. So now the other steady state should reach. There is a command to turn on the switch, means the diode has to turn off. So the current has to fall. So here current falls like this. It falls linearly and it crosses the zero thing. Okay. So the moment when the current crosses the zero axis, what people observed is that the voltage is unaffected, means there is a delay in the voltage. Okay, so what happens? This thing happens. Then the also current further goes and falls beyond this axis. So basically the current goes below the steady state value. The steady state value is here IL. This is IL. So it goes below this value, means it increases in the other direction like this. It goes on falling, and then it hits a peak value, and then again it goes like this and it hits the steady state like this. This is I leakage. Okay, so this peak value of current all the way from this point, that is from zero axis till this axis, is called as the IRR, means this phenomenon is called as the reverse recovery. Reverse recovery from the point when the current starts falling below zero till this point when this hits the steady state like this. So if you go on extending it down, so what happens when the current crosses zero, voltage is still unchanged, and this is the peak, negative peak of the current. Voltage here is still unaffected. Voltage will tend to fall only when the current crosses this peak point. So then the voltage tends to fall, but it should settle at this value, right? Minus V. But what people observed is that it goes and falls, and there is a undershoot here, and then this is minus Vin, this is the steady state value. It goes and then it hits like this. Means the moment current has attained steady state value, voltage also attains steady state value of minus Vin. So this whole is minus Vin, and then this is the steady state. And one thing, V forward is almost in the range of 1.2 volts for silicon power diode. Okay, so now in the turn off of the diode, there is a large undershoot in the current waveform. This is the IRR current. So let's define some times. So the time from which there is a off command for the diode till the point where the current crosses 0, this time let's call it T3. Next time is from this point to till the negative peak of the current, let's call it T4, and T5 is the remaining time, that is from the negative peak of current till the point where current and voltage both achieve steady state, let's call it as T5. And as I said, let's define reverse recovery from the point like this. TRR, reverse recovery, is the total time from the point where the current crosses the 0 until the current achieves the steady state. This is TRR. So TRR is T4 plus T5. So TRR equals to T4 plus T5. And T off, this is whole T off. That is from the point when it gets command till the steady state. That should be the total, ideally the total off time. So T off equals to T3 plus TRR, or T3 plus T4 plus T5. One more thing, the area under this reverse recovery region is called as the charge, because the integration of I dt is equals to a charge. This is called as the reverse recovery charge. Okay, this is minus Vin, and this is the undershoot in the voltage. Let's call it as the undershoot MP during off, MPV off. I'll tell you the notation why it's like this, MP off. MP is the overshoot or undershoot. V means in the voltage during the off time. This is MP off. This is due to the effect of the reverse recovery. Okay. So QRR is the reverse recovery. Recovery means this channel of the MOSFET, this in the construction diagram, the channel of the MOSFET means the state of the majority carriers in this different regions to diffuse and become in a steady state motion. That is called as the recovery, from on to off and off to on. The charge carriers will flow inside the different regions and to achieve some steady state during on and off time. That is called recovery. Forward recovery is when the time needed for the recovery for the charge carriers to form the necessary barrier during turn on, and reverse recovery during the turn off. So the QR is the reverse recovery charge. IRR is the peak reverse recovery current. Here I can write it as RR. Thus IRR is peak reverse recovery current. So you can say that QRR equals to integral I d dt, which is from time T3 to T5. Or if you just assume it to be a triangle, let's assume it is a triangle. So it's half into base into height, half into base is TRR, height is IRR. So QRR is TRR into IRR by 2. So these are the switching characteristics of a power diode. There is a there is a forward recovery effect in the voltage and the reverse recovery effect both in the voltage as well as the current. Here you can see that during the turn, means here there is no overshoot in the current waveform, but here there is a big undershoot due to reverse recovery, and in the voltage waveform there is a overshoot in during turn on and as well as overshoot during turn off, which you can see here. So this, let's call it as MPV. MPV on. This MPV on means the overshoot in the voltage waveform when turn on, and MPV off is the overshoot in the voltage waveform during turn off. Sorry, undershoot, not overshoot. So one interesting thing which was observed is that this MPV off is directly proportional to T4, T5 and the slope of falling of ID. Means here this slope, the rate at which ID falls, this is the slope, right? Like this is the slope. Means slope of ID means the type of the diode used. Is it a fast recovery diode or a Schottky diode or rectifier diode? So it decides the undershoot of the voltage waveform. So thus there is a term called softness factor. Softness factor S is defined as the ratio of T5 by T4. So if softness ratio S is greater than 1, so it means that there is a MPV of is less. When S equals to 1, it is called as a soft recovery diode. When S is greater than 1, MP is less, means it is a slow recovery. S equals to 1 means it is a soft recovery or optimum recovery. And for S less than 1, we have a high overshoot. MPV of is high. Means it's a fast recovery. Means if the gap, if T5 is greater than T4, so T5 decides the overshoot in the voltage waveform. As the reverse recovery charge, means this area under IC versus time graph is constant. So basically it's constant for a given diode, whatever the application it is. For a given diode, IRR and QRR is constant. So only T5, T4, the times or the slope of ID will decide the softness factor of the diode, and it depends on the application where we are using the diode. So when T5 is smaller compared to T4, it means that the T5 area is narrower, which means that more overshoot will tend to happen, because ultimately we have to make the areas equal. So if we assume it to be a triangle, so if the breadth is reducing, the height should increase, because half into base into height, this area has to be constant. And on a vice versa, if T5 is high, with the time is high, means it's a slow, time more means slow, then what happens, the overshoot is less. That's why the softness factor defines the speed of operation and the overshoot and the undershoots in the voltage waveform. So the two important aspects or the characteristics or the parameters of a power diode are nothing but QRR and QRR and TRR. Here TRR is reverse recovery time. So QRR and TRR are important. Okay, so these were the characteristics of a diode. So we started with the construction aspect of a power diode, the difference between this and the signal diode, the circuit representation, and the types of diode based on the voltage, current, power rating, and the speed of operation. Then we saw the VI characteristics or the load or output characteristics of a diode. It's very similar to a signal diode, and we saw the three regions of operation. Then we saw the on-state equivalent circuit of a diode. We saw that during the off time, there is some leakage current flowing through the diode, and during the on time or the conduction state, there is some forward voltage, on-state forward voltage, that is VF, across it. Then we saw the switching circuit. We created a test circuit by assuming a ideal switch and a constant current load or inductive load, and as it's an inductive load, it becomes a state. So first we draw on the steady state waveforms of the voltage and current through the diode. Then we saw the transients associated with it. We understood that there is a recovery happening at turn on and turn off of the diode. So overshoot happens during turn on forward recovery, and undershoot happens during turn off or reverse recovery. So the reverse recovery undershoot is critical here compared to the turn on. So turn off decides most of the speed of operation of the diode. So here I will write turn off decides the speed of operation of the diode. So it's important. So these things we have analyzed. So fast recovery diode is also called as snappy diode. So now we'll see the different parameters of diode. Parameters of diode as per the datasheet. So basically we'll segregate this type of parameters into three important regions, which is based on the VI characteristics. That is, we have three regions: breakdown, blocking, and conduction. So as per these three modes, we'll decide the characteristics. So first we'll see breakdown region parameters. So there are a few terms, manufacturer defined voltages that we will see is, so V capital R is nothing but the maximum DC blocking voltage. V RWM is nothing but the maximum working reverse voltage. VRSM is nothing but the maximum non-repetitive peak reverse voltage. Then VRRM is nothing but the maximum repetitive peak reverse voltage. Maximum repetitive peak reverse voltage. Then manufacturer defined VB, which is nothing but the breakdown voltage, or also called as the avalanche breakdown voltage. Then in terms of current, there is a current called IRM, which means maximum reverse leakage current. That is IL, which we saw in the previous thing. And energy rating, avalanche energy rating is EAVL, so that I will not write. So basically, what are these parameters that we see? Let's say that the voltage across the diode is as a square wave, because here you can see VAK. It varies from minus V into 0. So means it's basically a repetitive signal, right? And here this is the steady state waveform of the voltage across the diode. So assume that there are some overshoots across this repetitive waveform. So based on that, they have defined these parameters. Say this is time and this is VAK. Let's assume that the waveform of this is like this. First it was minus V. So let's say there is some this thing, and there are some glitches like this PK waveform. Then again it goes and hits 0. Like this, there are some glitches in the waveform, some peaks. And again it goes. So this type of thing, let's say there are two types of glitches, repetitive and non-repetitive. These are the repetitive thing. So there is some more like this. This repetitive pulses. So that's it. This is the switching frequency of operation, or 1 by f switching actually, because time is 1 by f switching, because I mentioned the time. So these are some repetitive spikes. So basically VRRM is nothing but the maximum repetitive peak reverse voltage. So first we have to see what are the types of the repetitive peaks. So these are the repetitive peaks. So this is VRRM, repetitive maximum repetitive peak reverse voltage. Reverse voltage we have to see, because voltage across the diode is nothing but the voltage during the blocking state or during the reverse stage. So these are the this is VRRM. Then VRWM. VRWM is maximum working reverse voltage. Maximum working reverse voltage means this thing. This should be the ideal steady state value, right? This. So this is VRWM. This is VRRM. This is VRWM. Now VRSM. Maximum non-repetitive peak reverse voltage. This is VRSM. From here to here. Let's draw it like this. So basically it goes on repetitive. Maximum blocking DC voltage, VRWM, RSM, RRM. VB is a background voltage. So background voltage we can't plot here. And IRM is the maximum reverse leakage current. This also we can't plot here. So this is nothing but the VRRM, RSM, VRWM. And based on the repetitive and non-repetitive glitches, we have this spikes. So these are given in the data sheets. If we draw this so if we saw that VRSM, so basically VB is the maximum possible voltage breakdown. So out of these 1, 2, 3, 4, 5, out of these 5 voltages, the voltage which has to be the maximum, what do you think the voltage among these 5, which voltage among these 5 should be maximum? I think it should be the breakdown voltage, because breakdown is ultimately beyond this, it will be avalanche. So I think VB should be the highest. Then after that, I think it should be the non-repetitive, VRSM. Because here you can see non-repetitive peak. So if this non-repetitive peak is greater than the repetitive peak, then VRSM is greater than VRRM. Else VRRM is greater than VRSM, but both are smaller than VB. So out of 4 we have plotted 3, and then the remaining one is VR, maximum DC blocking voltage. So maximum DC blocking voltage is what? Maximum voltage which it should block. So in this case, VRWM, that is the maximum working reverse voltage, is almost similar to the maximum blocking DC voltage, but we'll see that this is greater than VRWM, almost equals to VR. So this relation, if you plot as per the IV characteristics in the breakdown and the blocking region, I think this should be the blocking region, not the breakdown region. So breakdown and blocking region. Blocking region parameters. So if we just draw it, only the blocking characteristics, what we saw here is the current like this, it reaches and then it goes into avalanche breakdown. So the maximum, one second, is like this. So let's say that the maximum possible breakdown voltage here is VB. So this is VB from here to here. This is ID and this is VAK. This is VB. So VB is plotted, and let's say somewhere is VRSM, non-repetitive peak voltage. If the non-repetitive spike is more than the repetitive spike, then VRSM is greater than VRRM. Otherwise, it's vice versa. Similarly, let's say here there is something called VRRM, repetitive peak voltage, and then here somewhere is the ultimately what, VR or VRWM. Similarly, if you want to plot the current, it is this. What is the current? IRM or IL. IL means IRM is the nothing but the given by manufacturer. That's why I'm using the notation given as like this. But in the previous switch characteristics, I've written it as IL. So these are the parameters based on the data sheet of a power diode in the breakdown and blocking region. Then we'll see in the conduction region. Second thing in the conduction region or the turn on region. Conduction region parameters. So we have IF of AV, which is nothing but the maximum average forward current. So basically here why I have drawn a square waveform and not a sinusoidal waveform is because I have taken the example of this thing of a test circuit which is given here. Now this thing can be like this also, means let's say this is VAK versus time. So it can be sinusoidal waveform like this also. Like this. So it can be like this also. So this can be the VRSM. So these two are VRSM. This is V. This is the repetitive. This is the VRWM. RSM, RWM, and RRM. This is from here to here is VRRM. From here to here, or like this I'll draw. VRRM means the voltage across the blocking voltage nature of across the diode can be of sinusoidal waveform nature or square nature, but the ultimate principle of these blocking voltages remain the same. Then we'll see the conduction region parameters. IFAV is the maximum average forward current. IF RMS is nothing but the RMS forward current. IFRM is nothing but the repetitive forward surge current. IFSM is nothing but non-repetitive forward surge current. and Vf is the forward voltage, drop. So if we just draw the waveform of the ID, it is like this. Let's say it's like this, and there are some overshoots across it. So let's say this is IFSM. IFSM is nothing but the non-repetitive forward surge current. This is IFRM, from here to here. Then whatever is the average value of this is nothing but the maximum forward average current, and RMS value of this waveform is nothing but the the RMS forward current. So IF AB and IF RMS. AB means average, RMS means this value. So it has some average value. This is called as IFAV in bracket, and RMS value of it is called IF RMS. So in the IV characteristics, where to draw this thing? Let's draw it in the conduction region. In the conduction region, it's like this. This is threshold voltage. Beyond this, it's rising like this. Let's say this is ID and this is VAK. So the forward drop, let's say this is the forward drop. So this is VF, and again similarly the current that we are plotting is like this. This is the first current, then this is the second current. Say this is IFSM, this is IFRM, FSM, FRM, and then the average value of current is nothing but the based on the nature of waveform of it. So we cannot plot it directly on it, but somewhere we can show it is less than this value. So this is VF and the IFSM and IFRM plot in the IV characteristics of a diode. Okay. So apart from these voltages, in the turn off state, we have TRR, that is reverse recovery time, and QRR. So which I've already written, so I'll not write it again. IRRM is the maximum reverse recovery current, which I have written here. Peak or maximum reverse recovery current here, IRR. So one important thing that we observed in the diode is that the T of turn off, I think I have written it, turn off decides the speed of operation. Yes, here the turn off defines the speed of operation, means it decides the switching frequency. Of operation. It decides the switching frequency of operation. What? Turn off. So turn off is more important than turn on. So Fs is limited by turn off. Then one resistive characteristics of a diode as per turn off is nothing but the RT. So RT is nothing but the forward slope resistance. So if IV characteristic is like this, so if we draw like this, this is RT. RT. And the losses in a diode are also similar to that of a MOSFET, that is turn off, that is the loss, that is the conduction losses and switching losses. So total losses equals to conduction losses. Conduction losses means the resistive losses or the I square losses during the turn on process, means when the diode is turned on, and switching losses means the losses during the transients between, means the turn off time and turn on time. If you overlap the area and integrate and find the area under this, if you multiply this voltage and current graphs in the t on and t off time, and then if you see, add up them and means if you add up the products of this, then you will get the switching losses. So that is the switching loss. So on-set equivalent circuit of a diode, actually this is not F, this is VFCTO. So I forgot VFCTO is nothing but the threshold. VFCTO or VT, nothing but the threshold voltage. And turn on VF is nothing but the forward voltage drop of the diode. So we can write VF as VFCTO plus ID into RT if we have a simple approximation of it. So based on this, we have like this: VFCTO, this is RT, and this is ID. Means what is this? This is VF, forward drop, plus minus. So this is the on-set equivalent circuit of a diode. So in this lecture, we saw the introduction of a power diode, the difference between the signal diode, the types of power diode, its various characteristics, on-set equivalent circuit, switching characteristics, a test circuit with a state, that is an inductor current or a load constant current, its steady state waveforms, then transient waveforms separately, like ID versus time and VAK versus time. We saw the turn on and turn off delays and the reverse and forward recoveries. Then we have written the, based on the softness factor, we concluded that the speed of operation, the switching characteristic decide the speed of operation, and the choice of diode based on the application, and turn off decide the speed of operation, or it decide the switching frequency. Then we saw the different parameters of diode as per the datasheet during breakdown and blocking region, then during the conduction region, and the on-set equivalent circuit in terms of the datasheet defined parameters. So in the next lecture, we'll discuss the next power semiconductor device, that is a MOSFET. So thank you.